Hello, everyone, and welcome to this month's Insights and Practice webinar from Microbial Insights. Today, we're joined by Dick Raymond and Dr. Michael Lee from Terra Systems for this presentation titled Sulfidated ZVI and Carbon Amendments for Halogenated Solvents from Lab to Field Applications. Dick Raymond is the founder and senior consultant of Terra Systems, an environmental biotechnology company that is celebrating its 34th anniversary. During the past 40 years, he has designed and managed numerous successful in situ and ex situ soil and groundwater remediation projects all over the world. Dr. Mike Lee is the Vice President of Research and Development at Terra Systems and has over 35 years of experience assessing natural attenuation of organic contaminants and applying in situ bioremediation of chlorinated solvents, metals, hydrocarbons, and other contaminants in groundwater and waste impoundments. Dr. Lee has published over 100 articles in peer-reviewed journals, conference proceedings, and books. Today, we're talking about the synergies between abiotic and enhanced biotic remediation of halogenated solvents. Our speakers today have worked with us here at MI for many years, so I'm super excited to continue learning from their expertise and seeing how treatment strategies are developed in the lab and then transition to the field for real environmental impact. Before I hand this over to our speakers, I do just have a couple of reminders. First, at the end of this presentation, we will take our remaining time for a Q&A session. So please type your questions in the GoToWebinar control panel, and we'll get to as many of those as we can. This session is being recorded, and the recording will be available on our website as well as our YouTube channel in the coming days. You can also subscribe to our YouTube channel to keep up with future webinars as well as our MI video podcast series. Finally, certificates of attendance will be automatically emailed tomorrow to all attendees on the stream right now. Now, please join me in welcoming our speakers, Dick Raymond and Dr. Michael Lee.
Good morning. This is Dick Raymond speaking. I've been asked to give you a little bit of history on how we got to the point we are at with sulfidated ZVI. Terra was, as Hannah mentioned, was founded in 1992, and we're performed the Mike and I were part of the team that performed the first field demonstration of anaerobic bio of PCE when we were at DuPont, and that occurred at the Victoria, Texas facility of DuPont. Terra has the first EVO emulsified vegetable oil patent that was issued in 2002. We have a worldwide footprint. We've operated in Asia, South America, in addition to North America. One of the things that's not on this particular list is that we were one of the first licensees of the NASA emulsified ZVI patent in 2006. We have our own facility in Claymont, Delaware, which is just outside of Wilmington, where we make all of our products. We are focused on research and development, led by Mike, and in addition to the R&D function, we maintain a treatability study laboratory. We like to think we're one of the first green and sustainable remediation companies because of the products that we make and how we make them. And as a result of our manufacturing operations, we can control a number of different factors when it comes to making our products. Mike? We're going to be talking today about sulfidated zero valent iron and both the biotic dechlorination through the use of our emulsified veg oil products and the abiotic dechlorination. So we've got two technologies that are working on destroying the CVOCs, which creates lower reducing conditions, extends reactivity, and also provides some buffering. In terms of selecting a ZVI particle that for your particular site, A key issue is the remediation objectives. For the hotspot treatment areas, we're looking typically at a smaller ZVI particle down in the 4 micron range for the rapid reaction. And of course, for permeable reactive barriers, where we want persistence for an extended period of time, we'll typically recommend a larger ZVI particle. The largest ones we're using today is about 125 microns. Of course, the smaller the ZVI particle, the larger the surface area for reaction, and the reaction rates increase accordingly. We've been experimenting also with some combinations of different particle size irons. And one of the key learnings over the last years is the sulfidation impact on the reactivity of the iron, which Mike is going to go into in far more detail. And with that, I'm going to turn it over to Mike.
All right, thanks, Dick. So we'll be talking today about some laboratory batch and column studies and then some case histories. We're going to compare different sulfidated zero valent irons, different loadings of the iron and the substrates, incubation times, a variety of different contaminants, and with and without bioaugmentation cultures. So as Dick pointed out, for chlorinated ethanes, we're going from tetrachloroethane to trichloroethylene to cis 1,2-dichloroethylene. Often we see a little bit of trans 1,2-dichloroethane generated in that degradation product, and then it's going to vinyl chloride and then finally to ethene and ethane. Chlorinated methanes, starting with carbon tet, removing a chlorine to form chloroform, dichloromethane, and then chloromethane. Also be talking about chlorinated ethanes, 1,1,1 trichloroethylene, 1,1,2 trichloroethane. Those are degraded to 1,1-dichloroethane and 1,1-dichloroethene. Typically, when we see 1,1-dichloroethene, it's at sites that had the TCA, the chlorinated ethanes. We don't really see it very often at sites with just PCE or TCE. And the next step in the chlorinated ethane degradation is chloroethane. And then we're also going to talk a little bit about some brominated methanes, bromoform, dibromomethane, and bromomethane. And then brominated ethanes, ethylene dibromide, 1,2-dibromomethane, and that goes to bromoethane. So we'll talk about EVA loadings between 0 and 15 grams per liter, ZVI particles between 4 and less than 125 microns, loadings of ZVI between 3 to 10 grams per liter, sulfidation agents. I'll talk about this a little bit extensively, sodium dithionite, sodium sulfide, sulfur, calcium polysulfide, and then the ferrous sulfide solution. And then also bioaugmentation with either Dehalococcoides or Dehalobacter. So the first study we did was with just groundwater or with water. It was spiked with a mixture of PCE, 1,1,1-trichloroethane, 1,2-dichloroethane, carbon tet, and bromoform. So we have treatments including a control, SRS plus the bioaugmentation culture. The larger ZVI particles, less than 125, were added at about 10 grams per liter. And then one of the treatments we added 0.7 grams per liter of sodium sulfide. We also have smaller ZVI particles, 44, with and without the sulfidation agent, and then combinations with our emulsified oil and the ZVI. Everything's about 10 grams per liter of the ZVI and up to 15 grams per liter of the EVO. We bioaugmented most of the treatments. The SRS plus TSD was bioaugmented on day 7 or 12 and 43. And the other treatments were bioaugmented on day 43. And samples were collected over 70 days. For PCE, we're seeing removal of greater than 90% shown in green. However, the 44 micron was sulfide, and a little bit less for the other ZVI products. The best treatments for the 1,1 trichloroethane with a 44 micron ZVI with sulfide, and the SRS with 125 micron and ZVI and sulfide. 1,2-dichloroethane, the maximum removal we saw was 52%. Most of them were between 9 and that point. So we don't see as good removable treatment for the 1,2-dichloroethane. And that's pretty commonly observed where people have looked at using ZVI. Carbon tet, good removals in almost all the cases, with the best being the 125 micron ZVI and sulfide, the 44 micron with sulfide, and the SRS treatments that were also bioaugmented. And bromoform, see almost complete degradation, 97 to 90 or 100% with all the ZVI loadings. So very good treatment of the bromoform. The next is the soil slurry system, the soil from a site, about 43% by weight. We had control, 4 micron ZVI alone, and ZVI with sulfur, SRS, our emulsified oil with 4 micron ZVI with and without sulfur, and then also a treatment we did bioaugmented. The loadings here were about 10 to 13 grams per liter of EVO, and a little bit lower loadings of the ZVI between 3.1 and 6.7 grams per liter. And then the TSID was added about 1.7 grams per liter, and the sulfur at fairly low concentration of 0.2 grams per liter. We're seeing almost complete removal of the trichloroethane with the 4 micron ZVI with and without sulfur, and in that treatment with the SRS and bioaugmentation culture. Pretty good removal again for the TCE of up to 99%. And the chloroform, again, pretty much the same group of compounds gave you the best removal. And the boxes in green are 90%, in yellow 80%, and 70% for the blue. The third batch test, again, with just groundwater, the treatments included a control, 4 micron ZVI, less than 125 micron ZVI, 44 micron ZVI with sulfide, and then the combination of the SRS and the 44 micron. Most of the loadings of ZVI were about 10 grams per liter, with EVA loadings of about 15. And in this study, we used sodium thionite as the sulfidation agent. And this study was only sampled over 28 days, so a little bit shorter reaction period, and may not have been long enough to see more complete degradation. Started at between 0.84 milligrams per liter of carbon tet up to a maximum of 4.2 of ethylene dibromide. The PCE, we saw the maximum removal with 4 micron ZVI alone. And for 1 trichloroethane, that also did the best, and then the treatment with the 44 micron with sulfide. Carbon tet ranges between 64 and 79%. Bromoform, almost complete removal with the different ZVI particle sizes, and then very good removal of the ethylene dibromide. The next test was with groundwater. The treatments included a control, SRS plus the ZVI 4 micron with dihalocoides. We've added sulfate as a way to generate more sulfidation. And then we also had treatments with low SRS, moderate SRS, and moderate SRS was the dihalocoides. And these were sampled over 84 days. We're seeing TCE transformations up to 99.99% with the moderate SRS plus dihalocoides. We're seeing transformation of the DCE, and in some cases, say in the control, we're seeing that we're losing the VOS vinyl chloride, probably to abiotic reactions or such as volatilization. But we're seeing good removal of the vinyl chloride with the SRS, CVI, and sulfate, and the treatments with the SRS plus Halogenated. The sum of the chlorinated ethanes removal for the treatments with the SRSC and sulfate and the SRS and Halogenated range from 97.8 to 99.8%. And a little bit lower concentrations of chloroform, again, seeing very good removal for many of those treatments. A little bit better for the treatments with the ZVI than just the SRS. So in conclusions, the ZVI or EVO plus the ZVI did better typically than the EVO and bioaugmentation in these batch studies. In a field situation, I think we're going to probably see more degradation with the EVO and bioaugmentation cultures. We see that the ZVI and sulfidation agents increased the PC and TC degradation with good removal of the 1,1-trichloroethane, carbon tech, chloroform, bromoform, and ethylene dibromide with ZVI alone. And again, 1,2-dichloroethane was not treated as effectively. A variety of different sulfidation agents can be used. We've pretty much settled on the ferrous sulfide solution. It's easy to handle. It shows us good reactivity and longevity. So it's really what we're preferring or recommending, and it's easy for us to work with. It typically requires a low sulfur to iron, and it can work with the sulfidation can work with the small, more reactive ZVI to moderate and ZVI particles. We also use one of the biotraps from Microbial Insights. These were in situ microcosms that were baited with two different products. We have the SRS-Z sulfidated with augmentation culture and added a magnesium buffer, and then a treatment that was not sulfidated. And so we're looking at the numbers of dehalogenated and the reductases for TCE and vinyl chloride, the TCEA and the BVCA and the VCRA. Comparing the two different products, the sulfidation treatments have a little bit higher concentrations of dehalogenated and the reductases genes. We're seeing lower concentrations of the chlorinated ethanes in the sulfidated treatment versus the non-sulfidated treatment, and higher production of ethene and ethane. So, again, in a field situation, we're seeing the value of the sulfidation agents. Next, talk a little bit about a couple of different column studies that we've done. This is a column test that we did use with 130 micron ZVI, which were added at about 42 grams per kilogram, about 4% by weight. And we use calcium polysulfide as a sulfidation agent. And these studies, the retention time on the column was about 6.1 to 13 days. Initially, with the medium ZVI shown in black, we're seeing almost complete removal of the chlorinated ethanes on the left. And then over time, that extent of the degradation drops off, but we're seeing 99% removal of the chlorinated ethanes with the calcium polysulfide treated ZVI, and also for the chlorinated methanes, we're seeing very good removal. Column test 2, we had 5 different columns. We had about 10 grams per kilogram of ZVI with a low ferrous sulfide. We did treatments with the SRS plus ZVI with 15 grams per kilogram of SRS, 10 grams per kilogram of ZVI with a low ferrous sulfide solution and higher ferrous sulfide solutions to try to see what impact the value or the changing the ferrous sulfide solution might have on it. And these studies were run at a retention time of about 1.6 to 2.8 days. We did augmentation on day 15, and on day 17, we added some additional ferrous sulfide to the influent for all the columns. So we're upflows from the columns and collecting the effluents in Tedlar bags. So this shows the results for the chlorinated ethanes, the overall removal percentage, all the way to ethene. So we're seeing the best treatment with the SRS Z plus the low ferrous sulfide. Good removals with the treatments with the SRS, low ferrous sulfide and high ferrous sulfide, much better than the treatments with just the ZVI and the SRSZ without the sulfidation, which showed 50 to 80% removal. Chlorinated ethenes, again, poor response without the sulfidation agents. In this particular set of compounds, the ZVI with the low ferrous sulfide gave us a little bit higher removal than the other treatments. And then chlorinated methanes, carbon tet, the highest removals were with the treatments with the SRS with the low and high ferrous sulfide. And we see a little bit of improvement from day, say, 21 to 28 after we added the augmentation culture and the ferrous sulfide solution in those treatments with the ZVI, ZVI low ferrous sulfide, and the SRSZ. So kind of in conclusions for this particular column study, showing the components, retention times range between 2 to 2.9 days. We're seeing TCE removal of up to 98% with the SRS plus sulfide, low ferrous sulfide, and this is an average concentration over the time period. And we're seeing the chlorinated ethenes overall being reduced by up to 94%. The time to the TCE maximum contaminant level of 5 micrograms per liter ranged between 2.8 days to 11.8 for the ZVI. The 1,1,1-trichloroethane concentrations were between 0.7 and 3.1 milligrams per liter. The best treatment, again, on average, was the SRS-Z plus low ferrous sulfide, followed closely by the treatment for the SRS-Z plus the high ferrous sulfide. And the time to reach the MCL for those was about 0.8 to 4.9 days. Again, we're seeing a little bit better removal of the parent TCA than we are the total chlorinated ethanes. And then for chloroform, we're up to 98% removal of the chloroform on average with the SRSC plus the low ferrous sulfide. And then we're seeing, up to 92% removal of the total chlorinated methanes in those treatments. There's no MCL for chloroform, so we don't have a projection for time to reach that number for chloroform. So in conclusions, the ZVI and SRS ZVI treatments with ferrous sulfide were better than the treatments without the ferrous sulfide solution. The SRSZ with the ferrous sulfide gave the highest treatment of TCE 1,1,1-trichloroethane and chloroform over time. The augmentation and the ferrous sulfide and the influence seemed to increase dechlorination in that last time point. We're seeing somewhat less chlorinated intermediates with the ferrous sulfide addition to the iron, and enhanced VOC dechlorination with extent and degradation rates with the ZVI. I'm going to give you a couple or 3 different case histories. This is a project in New Jersey. There was a former manufacturing facility that's been closed for a number of years, and they wanted to redevelop it and put in a building that would generate funds for the county and the city. So we're dealing with overburden and bedrock compacted with chlorinated VOCs and 1,4-dioxane. The 1,4-dioxane was primarily dealt with in situ chemical oxidation. There's really not much degradation of 1,4-dioxane under anaerobic conditions. Primary VOCs were trichloroethene and 1,1,1-trichloroethane. The overburden is a silt and fine sand, and then a sandstone bedrock. So this is in the overburden. There are 2 areas of concern. The seepage velocity range between 2 and 40 feet per year. We used a variety of different products at this particular project, from a small droplet EVO, the SRS SD that has a particle size of about 0.6. We had an EVO plus sulfidated ZVI, with 4 micron bioaugmentation with both the D. halocoides and D. halobacter. In this particular project, we also added a nutrient blend that contains nitrogen, phosphorus, and sulfate. And that sulfate is going to help to generate the ferrous sulfide. These were injected into the overburden with direct push. So we have hot grid shown in blue, and then permereactive barriers shown in the orange. And there's about 1,100 linear feet of permeoreactive barriers, a total of 150 injection points. So this shows the results for some of the wells. MW17DO, we're seeing 78% removal of the chlorinated ethanes over the 2 years of monitoring, seeing up to 98% removal in MW13, and even 80 feet down gradient in MW31, we're seeing 99% removal of the chlorinated ethanes. So seeing a combination of the biological degradation with the production of DCE in vinyl chloride, whereas at MW13D, we're seeing more of an abiotic signature with the simultaneous reduction of the cis-DC and TCE, although we do see a little bit of vinyl chloride shown in pink. And these graphs are shown on a micromolar basis. For the chlorinated ethanes, we're starting with the 1,1 trichloroethane, and we're generating some chloroethane in MW13 or 17DO. We're seeing only about 6.3% removal of the chlorinated ethanes as the chloroethane is persisting. But there is some evidence at the latter time frames for that's to come down. We're seeing degradation rates between chlorinated ethanes between the 6.3 to 92.1% in the overburden. In the bedrock, focused on treating fractures, we used a large droplet EVO that's going to be retained more in the fractures. We used 2 different types of EVO and sulfidated ZVI. We used 11% of a 4 micron to generate more rapid degradation, and then 89% of the 44 micron to give us a little more longevity and also at a lower cost point. Bioaugmentation with D. halocoides and D. halobacter. Again, the nutrient blend of nitrogen, phosphorus, and sulfate. And these were injected into 13 open hole bedrock injection points using stratopactors to target identified fractures. So over 24 months, MW4BR, we're seeing 94.3% removal of the chlorinated ethanes, 99.9 or 5% in 16BR. So very good removal of the chlorinated ethanes. Chlorinated ethanes actually seeing better removal in the overburden, up to 88.8% in MW4BR and 99% in 16BR. Again, we're seeing some production of the daughter products, but then the chloroethane concentrations are coming down. So in conclusion, this was a fast-track project. There was some uncertainty from the limited characterization up front. The contamination area and concentrations were reduced site-wide. Treated a large plume with ongoing treatment with single injection events for enhanced in situ dechlorination. And to be able to construct a building and get new tenants into the building, creating jobs and municipal revenue. The next case history is a contaminated site which on Long Island extends from 10 to 80 feet below ground surface. It's an overlying sand with a confining clay at the bottom, with DNAPL PCE found at the clay surface. So the objectives were to try to inject in the top foot of clay and the 4 feet of the overlying sand to try to treat that DNAPL, and they wanted a material that was going to stay in place and not be washed out. A treatability study was done by others that showed that the combinations of the SRS, NR, ZVI, so that's a large droplet with an anionic surfactant, was better retained than our standard SRSZ product with a large droplet with a non-ionic surfactant, or the combination of EZVI, which is soybean oil, surfactant, and ZVI doesn't include the nutrients. So the SRS NR worked better for this particular treatability study. So a pilot was done into 2 wells, our IW 101 and 102, injected about 7,400 pounds of sulfidated SRS NVI, 20%, 4 micron. Also, it did add some additional sulfidated 5 micron ZVI and glycerol, 30,000 pounds of sodium bicarbonate, 10 liters of the TSI DC bioaugmentation culture, and 10 pounds of sodium ascorbate, which we use to generate reducing conditions for the bioaugmentation culture, and a total injection volume of about 5,900 gallons. So this shows the maximum TOC around both of those injection points. We're up to 11,500 milligrams per liter around IW 101. We do see pretty good distribution out to 201, 1,800 milligrams per liter, and 202 on the around PTT, our IW 102, again up to 40 or 21,000 milligrams per liter of TOC, and pretty good distribution. The chlorinated ethane shown on the right, we're seeing 90 to 99% removal around IW 101, and up to 98% removal around IW 102. The next slide shows a little bit more data. So we're seeing TOC distribution around 101, and the injection volumes there were a little lower, only could get about 2,000 total volumes or gallons of material in the material. And we're showing TOC concentrations up to 11 feet out from that point. Not quite as much removal of the chlorinated ethanes at that well 201. We do see pretty good degradation of the chlorinated ethanes at well 204 and chlorinated ethanes. And there's also some 1,2-dichlorobenzene present at the site, and we're seeing good treatment of that in well 204, which was the only one that showed around 101. Around injection well 102, up to 21,000 milligrams per liter of TOC. And we're seeing distribution of TOC out to 18 feet from that point. Good removals of the chlorinated ethanes of 55 to 98%. Again, good removal of the chlorinated ethanes except at well 208, and some degradation evidence for 1,2-dichlorobenzene also. So the lab study showed the custom blended SRS ZVI with the anionic surfactant and ferrous sulfide solution stayed in place, promoted chlorinated ethane degradation where TOC distributed up to 11 to 18 feet from the injection points. There's evidence for chlorinated ethanes and 1,2-dichlorobenzene destruction, and a full-scale system design is underway, and we expect that to happen later in the fall of this year. The third case history is a site in Central Florida. So we're dealing with 3 zones: an A zone, which is 28 to 38 feet below ground surface. It's primarily sand. Between 37 and 55 feet is the B zone, which is a sandy clay, and underlines that between 65 and 75 feet is a limestone bedrock. So we're seeing high TCE and daughter products used a combination of small droplet emulsified vegetable oil, large droplet emulsified vegetable oil, the 5 micron material, and the EVO with the 4 micron CVI sulfidated augmentation, and then a combination of sodium bicarbonate and calcium carbonate as buffers. In the A zone, the SRS FRL, the large droplet material, was ejected in the surrounding areas, and then those are in purple. And then the green is the EZVI, which in this case was actually the SRS ZVI. So a total of 37 points injected on a 5-foot radius of influence with the SRS ZVI, and 31 for the FRL. In May 23, they came back and did some additional injections of the SRS FRL to some of the zones that had not received as good treatment before. They looked for the presence of the EVO in wells that were collected about 10 feet from the injection point at depths of 10 to 15, 15 to 20, and 20 to 25. And they saw the EVO in the soil cores, and they also took samples and diluted them 1 ounce of soil to 3 ounces of water, and saw the EVO in the water standing over those. They also looked for the EVO and EZVI in the soil, and were able to detect that. So this is the results for the A zone, 28 to 38 feet below ground surface, and MW101 that was treated with the SRSZ. We're seeing 44% removal of the chlorinated ethenes with a maximum of about 1,800 milligrams per liter of TOC. We do see some increase in vinyl chloride and some chlorinated ethenes at the final time point that data was collected for in December of 24. So it appears that some additional amendments might be valuable here. In MW104, which was treated with SRS, we're seeing 86% removal of the chlorinated ethenes. We're not seeing a lot of vinyl chloride being produced in this particular well. And then the B zone, the sandy clay, between 37 and 55 feet below ground surface, did both the combinations of the SRS FRL, the large droplet, on a 12-foot radius of influence, a total of 21 injection points, and then the small droplet SD. These were injected with an angle approach to try to get underneath some of the roads in areas that weren't accessible for direct push injections. So in May 23, we came back and did some additional injections of the FRL, and then also in February 24. So these shows the results for MW101 that's treated with the SRSZ. Overall, 99% removal of the chlorinated ethenes, up to 250 milligrams per liter of TOC, shown in the gold line. And we do see some ethene generation shown in the black line on the left, although the data was not collected for ethene after that time point in MW101. MW65B with SRS, we're seeing up to 2,000 milligrams per liter of TOC, and a removal of the overall removal of the chlorinated ethenes of 73% from the peak concentrations. In the limestone bedrock, high concentrations in certain areas, and that's where they use the EVZVI on a 5-foot radius of influence, total of 4 injection points, and the surrounding area around that use the FRL. So additional injections in May 2023. This shows the results for MW65C, an area that received the SRSZ. We're seeing 95% removal of the chlorinated ethenes with only up to about 50 milligrams per liter of TOC. So good treatment in all 3 zones. The A zone, we're seeing a decrease in the sum of the chlorinated ethenes of an increase of minus 484 to 99%. And that well 103A appears to have DNAPL concentrations, which cause the concentration to come up. The B zone would decrease of up to an average of 67%, ranging between 0 and 100%. And then the C zone range from 20 to 95%, average of 58%. So in conclusion, sulfidation increases the reactivity of the ZVI. It works with a variety of ZVI particles. Several forms of sulfur are effective, can be used with EVO and augmentation, and the case history showed the effectiveness of this approach. I'd like to acknowledge some of the companies that provided the information for the case histories: Isotech, TRC, Root Associates, and Geosyntec. And at that, I'd like to be willing to take any questions that you might have.
Great. Thank you so much, Dr. Lee, for this talk. I really appreciate seeing these kind of combined approaches, both the abiotic and biotic pathways. I see it not only as like kind of, I see it as kind of not putting all of your eggs in one basket using these like multiple strategies, but it's even more like getting your eggs in baskets to work together, right? So thank you for your expertise and your insights on that. As far as questions from, and I will say that we are getting a lot of comments about this educational talk and everything that folks have learned from it. But as far as questions, to jump into a Q&A, first, if we could just revisit, could you mention which sulfur additive you said that you were recommending? We just had a speaker who missed it, so we wanted to clarify.
We're primarily using the ferrous sulfide solution. It comes to us pre-mixed, so we just add that with our emulsified vegetable oil and ZVI powder. It has worked well for us in both our batch and column studies as well as field projects.
Perfect. And I do have one attendee who's asking a 3-part question. Now, I do have, I am waiting on parts 2 and 3 to come through, but we'll get started on the first part of their 3-part question. First, they said, of the several sources or forms of sulfidizing agents that you tested, which performed best in sulfidizing the ZVI, and how did you confirm the extent of that?
We didn't do any testing to confirm the sulfur content on the ZVI. We're just looking at the effectiveness of those amendments in destroying the VOC contamination.
Got it. Okay. I have another question asking about, well, first saying thanks for a really interesting talk. But then as far as their question, you mentioned chlorinated benzenes. Have there been any studies, or do you have further experience regarding these ZVI approaches with chlorinated benzenes?
We saw 1,2-dichlorobenzene in that one study from Long Island, and it did appear to have some effectiveness there. We're actually doing a microcosm study now where we're evaluating a different bioaugmentation culture, specifically DRESS chlorinated benzenes. We have 1,2-dichlorobenzene, chlorobenzene, and we're going to be following the degradation pathway there. The culture that we're typically using, the TSIDC, probably has some effectiveness against chlorobenzenes, but it's probably not going to get you to complete degradation. So this second culture appears to have a lot of potential for that process, and so kind of a wait to hear study.
Definitely more to come. One question we have is, did you test gas generation such as methane after the amendment applications in these studies?
And yes, we are measuring methane, ethane, and acetylene gases. I didn't show any of the methane data. We are generating, methane, both from the biological degradation of the emulsified vegetable oil. You may get some methane from chlorinated methanes, the carbon tetrachloroform, but it's almost impossible to distinguish where that methane's coming from. And when we've looked for acetylene and we've seen it at fairly low concentrations, it's not a major degradation product that we've seen in our lab studies. As far as I know, none of the field projects have actually looked for acetylene, but it is an abiotic, a fairly signature compound from the ZVI.
Great. I have a follow-up to that earlier 3.3 part question that I mentioned about what is the optimal or required molar mass ratio of sulfur and iron for optimal sulfidation or sulfidation?
I mean, it's usually pretty low, and I don't remember the numbers off the top of my head, but probably 1 to 10% of the iron content. Typically, we're using 1% of the ferrous sulfide solution, or 10% of say if we're adding 40 grams per kilogram of the ZVI, we'd add 4 grams per kilogram for the ferrous sulfide solution.
I have a question about DNAPL. So you mentioned the challenges of DNAPL being present. Is there a limit to the starting concentration of chloroethanes in groundwater beyond which ZVI is not going to be an optimal technology? So is there like a concentration?
And no, there's not, to my knowledge. Terra Systems was involved in a project over in the United Kingdom called the Sabre Project, where we were dealing with a DNAPL TCE spill, and we were able to demonstrate that with the addition of biomutation culture and our emulsified vegetable oil, we were able to degrade the TCE. We did see some production of ethane, and we saw a lot of daughter products. So, successful demonstration of DNAPL TCE degradation, and the combination with the zero valent iron is going to give you both the abiotic and biological degradation rates. So that's definitely going to help.
I did have one question about a site's naturally or like baseline iron and sulfur concentrations. I'm curious if those initial concentrations affect like the marginal benefit of the added sulfidation, or if you saw kind of just a net positive across the board for the added sulfidation with the ZVI.
I mean, definitely see a benefit. If your groundwater has elevated sulfate concentrations of, several hundred micromilligrams per liter, then as the sulfate's reduced to sulfide, it's going to coat the ZVI and it's going to give you some sulfidation. I mean, we did one of the studies where we actually saw, we added some sulfate, and it did seem to promote the extent of degradation of the chlorinated ethanes. So, when you're looking at ferrous sulfur or looking at iron in the system, typically under oxidative conditions, you don't see much, or you may see total iron, but you don't see much reduced iron. And when you add the substrates, then you start to produce ferrous sulfate or ferrous iron. And so it's hard to know how much that's going to happen before substrate injections occurred.
Got it. I think that you mentioned that a lot of these studies were focused on total contaminant reduction. Do you have any insights on the relative contribution of each of these pathways to total contaminant degradation, or were we solely focused on total?
I mean, some of the treatments in the laboratory experiments looked at, individual components, say the emulsified vegetable oil, and then treatments with emulsified vegetable oil and the zero valent iron. And so you can kind of back out, what impact those treatments had.
Got it, for sure. Okay, I am not seeing any more questions rolling through. Back up, I have one more that just came in. I have for case history 3,
Yes.
in one of the A-zone wells, monitoring well 101A, vinyl chloride and the sum of chlorinated ethane concentrations kept increasing. What might be the cause of this?
I think it just needed another round of amendments. And that area was beneath the building, so it was difficult to access. So, I mean, they may not have had access to be able to get to the second round of injections area.
Right, like we've always heard that remediation is a contact sport, so you got to be able to get that access.
Right.
All right, let me make sure we've got nothing else coming in. One more. From a toxicology perspective, traditionally vinyl chloride was seen as worse than TCE, but more recent studies in the US seem to have shifted towards TCE. Is this a correct understanding, or just a trend in the research or regulatory ways of thinking about it?
I'm not familiar with that, so I can't really comment.
Definitely fair. It also could just be, focuses and perspectives ebbing and flowing over time. So totally understand there. Like I said, I'm not seeing more questions come in. So I think we'll be good to wrap up here. As I mentioned, we will have certificates of attendance automatically emailed out. Those will go out tomorrow morning. And a recording of this webinar will be available on our website, most likely by the end of the day, on our YouTube channel closer to the end of the week. So this will be available for you to revisit and continue to learn from over time. Thank you, Dr. Lee and Dick Raymond, for your time today, for these lessons and insights, and for your work with MI over time and just your contributions to the field. We're very grateful for the time you take to share your knowledge with us in this format.
And thanks for the opportunity to give this seminar.
All right, I'll close this out today. Thank you very much.
Thank you.
All right.